Here's a problem that uses partial derivatives. So you're standing on a surface where the height is given by function of x and y, so f of xy is equal to 50 plus xy minus 3x plus 1/4 y to the fourth. Assume the positive x-axis points east and the positive y-axis points north. Part A asks to find and classify all critical points of f. Part B states that we're standing at a particular point on the surface. At this point, if you are facing due east, the slope is -1, and if you face due north, the slope is 2. So we want to find the equation for the tangent plane to the surface at this point. So starting with first things first, part A, we want to find and classify all critical points of f. So what we want to do first is find f sub x, which is the partial derivative of f of x and y with respect to x. So we treat y as a constant. Just a note, a function of x and y can also be written as z. Writing this function in its derived form with respect to x, and leaving y as a constant, the derivative of 50 will always be 0. The derivative of xy, if we treat y as a constant, let's say it was 3x, and we'll say now we have yx. The derivative of 3x is 3, the derivative of yx is y. Derivative of negative 3x is minus 3, and since y is a constant, we just get rid of this entire part here. F sub y, now we treat x like a constant. 50 is still just a constant, so it goes away. Now we have xy, that's like 3y. We would end with 3 in that case. So here, we end with x. Minus 3x, that's just like a constant, so that goes away. And 1/4 y to the fourth, we just derive like usual. That gives us a minus y cubed. So the problem says critical points. What do we want to do when we find critical points? Well, we derive, like we did here, the two partial derivatives we have. But critical points indicate finding some sort of maximum or minimum value. We set it equal to 0 in both cases. So y minus 3 is equal to 0. Y equals 3. X minus y cubed equals 0. We know y equals 3. So x minus 27 equals 0. X equals 27. Our critical point is therefore 27, 3. But we also want to classify the critical point, because we don't know if it's a maximum, a minimum, or something else, maybe a saddle point. So to do this, we do our second derivative test, which is d, capital D. This is equal to fxx, fyy, minus fxy squared. So first we'll find fxx. So we'll partially derive with respect to x. F sub x, we have no x's in f sub x, so all of these components are simply treated as constants, so fxx equals 0. Fyy, the x is treated as a constant, so it goes away, but we have minus y cubed, so we get minus 3y squared for fyy, and fxy, which is equal to fyx, we'll just use the fx and find fxy. So derive fx with respect to y, we just get 1, because all we have is a 1y. The constant goes away, because the derivative of a constant is 0. So d is equal to 0 times negative 3y squared minus 1 squared. D is equal to negative 1. D is less than 0. Thus, we know we have a saddle point as our critical point. So there's a saddle at 27, 3. Now here, we're given a situation, so we'll draw our axes. So positive y is north, positive x is east. If you face due east, the slope is -1, and if you face due north, the slope is 2. So if we're facing north, that's the positive y direction. So because we're on this surface, and we have these slopes, we know that the east is the x direction. So if we have a slope of -1 facing the positive east direction, that tells us that the slope with respect to x is -1. And if we face north and the slope is 2, this is the y direction, so the partial derivative with respect to y, or the slope with respect to y direction, is 2. We also know that fx from this previous slide is y minus 3, and fy is x minus y cubed. So -1 equals y minus 3. Y is equal to 2, and 2 is equal to x minus y cubed. So 2 equals x minus 8. 10 is equal to x. So now we need to find the equation of the tangent plane, and this, again, something like that needs to be memorized, because we have z is equal to f of x, y, plus the partial derivative with respect to x times x minus x naught, plus the partial derivative with respect to y times y minus y naught. Z is equal to f of x, y. We have our point 10, 2. This is our x, this is our y. So f of x, y, we have 50 plus 20 minus 30, so that's 40, minus 1/4 times 2 to the 4th. That gives us 36, plus we have our partial derivative with respect to x equation, plugging in the point we have. So the partial derivative with respect to x, plugging in 10 as x and y as 2, we get 2 minus 3, which is a -1, times x minus x naught here is 10, plus the partial derivative of y. We have an equation and we have a point. Plugging in x and y, we have 10 minus 8. That gives us 2 times y minus y naught, which is 2. Our final tangent plane equation, 36 minus x minus 10 plus 2 times y minus 2. That's the equation of our tangent plane at the point that we found, 10, 2.